Now in this video we're going to look at the contingency table approach for testing for population proportions being equal or not, and extend it from just two groups to several groups, say number of groups being equal to C. So contingency table approach, same approach like before, except that now instead of just having group 1 and group 2, you have up to group C. And these are the observed frequencies, x sub 1, x sub 2, all the way through x sub C, with sample sizes n sub 1 through n sub C. And we can find the individual proportions by dividing x sub 1 by n sub 1, x sub 2 by n sub 2, and so on. Of course, the number of items not of interest would be the difference between these two. Okay, now when you sum across like this, you get the total successes. So the x over n will give you p bar, and this will be 1 minus p bar. Yeah. Now these are the observed frequencies. Now with the p bar, when you multiply each sample size with p bar, you get the expected frequencies for the first row. And you do the same thing, take each sample size and multiply by 1 minus p bar, and you get the expected frequencies for the second row. Once you do that, then you have the observed frequencies, then the expected frequencies, then you can set up the chi-squared test. And of course, all the expected frequencies must be greater than or equal to 5. So let's look at an example now. Okay, in this example, we take the same approach, but here we are looking for satisfaction survey, whether the customer is satisfied or not, and we have 3 different hotels where we take random samples, okay, and these are the sample sizes, and how many of them said that they were satisfied, and how many said no, not satisfied. Okay, now we want to test whether pi sub 1, pi sub 2, and pi sub 3 are all the same or not. So let's go to the Excel file. So the groups here are the hotels, and there are 3 of them. Items of interest is whether a guest expresses satisfaction with their stay and express a likelihood of return. So we have 3 different population proportions now, pi sub 1, pi sub 2, and pi sub 3. Each is proportion of guests expressing a likelihood of return for each of those 3 different hotels. So the hypothesis that we're going to test whether all the pi's are equal or at least one is different. So not all proportions are the same, and let's assume 5% alpha. The data given here are sample size is 216. Of that 216, 128 said they will return. We have 232. Of that, 199. We have 252. Of that, 186 said they will return. So not returned then is that minus that. Okay. Now if you sum across like that, that gives you the overall number of favorable responses. Okay. And you do the same thing for the second row, you get the number of unfavorable responses. And if you add the 2, that will be your total sample size. Of course, you can add this way also, you get the same number. So now if you take the overall yes responses and divide by the sample size, we will make sample size absolute reference so we can copy. That's p bar and 1 minus p bar. So now what we have to do is to multiply each sample size with p bar and then with 1 minus p bar, which is that cell, and you will have the expected frequencies. So let's use absolute references judiciously. So here the sample sizes, they're all in the same row. Row shouldn't change, but the column should change. So if you say, okay, so row gets a dollar, not the column. Okay, times the P bar value. So P bar here, okay, P bar should always come from column G. Row should change from 48 to 49. So G gets the dollar, not 48. Now if you copy that down, and let's format for decimal places. One decimal place is good. And put the border back. Now if you copy across, you get the absolute expected frequencies. And if you sum this way, you should get the same row total as here. Okay, so the row totals are good. Then if you sum this way, you should get the column totals, and that should match. Okay, and all the column totals and row totals match, and all the expected frequencies are greater than or equal to 5, so large sample is satisfied. Now we can compute chi-squared, which is observed frequency minus the corresponding expected frequency, and that difference must be squared divided by the expected frequency, and that is for one particular cell. And now you copy that across the 3 hotels, and then next row, let's put the border back. So now if you sum, okay, that's your chi-squared statistic. Okay, the degrees of freedom is the number of groups we have. So let's do count A. Number of groups is the number of hotels minus 1. C minus 1 otherwise. Number of groups minus 1 is the degrees of freedom. Now we can set up the chi-squared table value, chi-squared dot dist dot rt, chi-squared dot inv dot rt, alpha, comma degrees of freedom. So that will give us the chi-squared table value. Okay. Now let me show you how to find the chi-squared table value from the textbook. So chi-squared table is here in page 525, and you have the degrees of freedom, and you have the upper tail given here. Okay, here upper tail is given here. So upper tail 5%, 10%, 0.025, 0.1% here, and 0.5%. So we want alpha 5%, degrees of freedom of 2 gives you 5.991, which is what we have here. So the conclusion then is to reject because our chi-squared stat is greater than the table value. And we can use the p-value approach, which will be chi-squared dot dist dot rt and chi-squared stat, comma the degrees of freedom will give you the p-value, and it is nearly 0. So p-value less than 5%, so reject H sub 0. So we have sufficient sample evidence to conclude the proportion of guests expressing a likelihood of return for these 3 different groups, 3 different hotels. They are not all the same. The probability that we are wrong, we are committing type 1 error, is nearly 0.